Hello everyone, and welcome to this presentation, which is all about the factor theorem and remainder theorem. So similarly to when you divide a value by a number, you get a remainder. You can do something similar with algebra. So in this session, we're going to take a polynomial function f of x, and we are going to divide that polynomial by x minus a, and it will have a remainder when we do that, and our job is to find that remainder. And we're going to do it by finding the value of f of a. Now that's a bit algebraic and a bit general, so I think the best thing to do is to look at a real example. So this is for your notebooks, and the example that we're going to do is we're going to find the remainder when 3x cubed plus 8x squared plus 3x minus 10 is divided by x plus 3. So we need a value of x that we're going to place into our polynomial in order to find the remainder, and the way that we do that is we find the value of x that makes x plus 3 equal to 0. So that value of x would be minus 3, and then simply take that value of x, put it back into the polynomial, and the value that comes out will be our remainder. So here is the working out for that. Again, brackets are useful when you are doing this on paper, so you can then see where the negative terms are and when the positive terms are, and it works out that if you work through the maths you end up with a value of minus 28. So when you divide 3x cubed plus 8x squared plus 3x minus 10 and you divide that by x plus 3, you will get a remainder of minus 28. Okay, good. So on this second slide, and this is for your notebooks as well, we're going to look at a special case of the remainder theorem. And that special case for the remainder theorem is when you get a remainder of 0. And if you do ever get a remainder of 0, then it's a bit like when we get a remainder of 0 using numerical values. It means that it is a factor. So it's just the same as using the remainder theorem, but we're looking out for an answer of 0, which will then tell us something slightly more interesting than when you just have a non-zero value for the remainder. So here is our question, and it's a show that question. So with a show that question, we have to make sure we show lots and lots of working, because we are being told that something is true, and our job is to prove it. So we're going to do it in exactly the same way as we did with the remainder theorem. So we are going to find that value of x that makes x minus 4 equal to 0, which of course is 4. And then we're going to take that value of 4 and we're going to place it into our polynomial. Now we know already that we are expecting a value of 0. We're not expecting a remainder because we are being told that it is a factor. So let's just do the maths on that. So I'm putting x is 4 into the expression 4 squared minus 2 times 4 minus 8 does indeed give me an answer of 0. And therefore we would finish the question off by reiterating what we were already told, that because there's a remainder of 0, so that's your proof, if you like, that it's a factor. Because we've got a remainder of 0, it means that x minus 4 is a factor. And that line at the bottom is needed for you to get full marks. If you just wrote the line above where you're proving that it equals 0, you'll get some of the marks, but you need that final sentence which talks about a remainder of 0 in order to get that final mark in the question. So please make sure you finish it off properly. Good, so as ever, it's your turn now to practice those skills. So in your textbooks, if you turn to page 24, there's an exercise that is devoted to looking at the remainder and to also look at what happens when the remainder is 0, and therefore proving that sometimes we have factors. So have a go at that exercise. Any problems, get into contact with your teacher to sort out any problems that you might have, and then when you're ready to move on, you can flick on to the next slide. Okay, so now that you've completed that exercise, you've had plenty of practice in the remainder theorem and factor theorem, and now we're going to move on to this example where we're using those skills to find the 3 factors of the cubic equation. We could also apply this to find 2 factors of a quadratic, or 4 factors of a quartic. So the skills that we're doing for this cubic can also be used for other higher order or lower order polynomials. So what we're going to do to find the 3 factors is we're going to look at different values of x, put them into the polynomial, and those ones that make the polynomial equal 0, well, they will be our factors. So it's a bit of a trial and error method for the time being, and then later on in the presentation we'll look at an example where it uses a more mathematical approach. So let's start by being fairly systematic, and we'll start at 0 and then followed up with 1, -1, 2, -2, and so on. So we'll start with 0, and you can obviously work these values out as well just to make sure you're happy with them. But when x is 0, the polynomial equals -15, so no factor here. Remember, we're looking for a value of 0. If we place the value of 1 into the polynomial, we get a value of -24 as a remainder, so not a factor either. But when we use the value of -1, then we get our remainder of 0, and of course that's exactly what we're looking for if we are trying to find factors. So the value of -1 gave us an answer of 0. What would be the factor? Well, it's almost like we have to do the reverse of what we did in the previous slides. So if the value of -1 gives us an answer of 0, then x plus 1 is our algebraic factor. That's what we're looking for as an answer. And then it's just a case of performing the same again, but for different values of x until we find the 3 factors that we want. So if we try a value of 2, we get a remainder of -21, so not a factor. When we try -2, we get an answer of 15, so again, not a factor. But when we try a value of 3, then we get a remainder of 0, so there is our second factor. So what would the factor be? Well, we work backwards, and the bracket would be x minus 3. So x minus 3 is our second factor, so I can place that at the bottom, along with the x plus 1 that I've already found, and then we carry on. So I've stepped up a little bit here. -3, 4 and -4 don't work, but you can prove that for yourself. When you try a value of 5, we get 120, so that doesn't work. And then finally, when we try -5, again, we get that value of 0. We get a remainder of 0, which means we have our third factor. So what would that third factor be? That third factor will be x plus 5. And that completes my factorization of the cubic, and we have 3 factors. They are x plus 1, x minus 3, and x plus 5. And you could check to make sure that that works by expanding the 3 brackets and proving that you get back to the original cubic. Okay, good. So that's a method that we could use to find the 3 factors of a cubic. But it's a little bit trial and error. It's not very methodical in that it doesn't get to the values quickly, and in some cases it could take you a very long time to find the factors. So instead, let's try and look at a different example where we are a little bit more mathematical. So here we have a different cubic, x cubed minus 8x squared plus x plus 42. And we are going to factorize it once again into 3 factors. And this is how we would go about it. So number 1 is we start by finding one of the factors. So this is trial and error still, but we only need to find 1 using trial and error rather than 3 like we did in the previous slide. So if we substitute -2 into the cubic, we get a value of 0. And therefore, as a result, it means that x plus 2 is our first factor. So I am going to write my cubic as x plus 2, which is my first factor, and then I am left with a quadratic, because if you multiply a linear bracket x plus 2 by a quadratic bracket ax squared plus bx plus c, that's going to get us back to the cubic that I started with. And my job now is to find the values of a, b and c. So we'll start with finding the value of a. The only way that I can possibly get a value of x cubed is by multiplying the x in the first bracket by the ax squared in the second. That's the only way when I expand those two brackets I'm going to get an x cubed term. So that means straight away that I can say that a is 1 because x times x squared gives me the x cubed that I need. So I've then gone on to the second line, and you can see that I've just simply replaced a with 1, and I found one of my three unknowns. The next value that I'm going to try and find is the value of c, because the only way that I can possibly get a numerical value without any x's coming out of this expansion is when I multiply the 2 in the first bracket by the c in the second bracket. And that has to give me an answer of 42. So that means that c is going to have to equal 21. So you'll notice I'm doing this a step at a time, and each time I'm finding a new value, I'm writing out a new line. I'm not trying to do this all in once. I'm writing it out step by step where I've replaced a, and then I've replaced c, and now my final job is to find b. And generally a, c, b, if you're going to use this method, is the way that I work out my values. A first, then C, and then B. Now B is slightly more tricky, so I shall talk you through this. So if I was to expand the brackets that I've got so far, this is my expansion that I achieve. So I've got the x cubed, I've got the 42 at the end, but I've also then got a mixture of x squareds and x's in the middle. So if I concentrate on the x squareds, I've got a bx squared here, and I've got a 2x squared here. They're the only x squareds in the expansion of the two brackets. And then if I look at my original cubic, I can see that the value of x squareds in the original cubic is minus 8x squared. So I need the bx squared plus the 2x squared from my expansion. That has to equal the minus 8x squared that's in my original cubic. Or more simply, if I take the coefficients of b plus 2, they have to equal minus 8. And now a little bit of maths on that, and I can see that b has to be minus 10. So I've replaced the b with minus 10, and now I have my quadratic bracket. And then there's one final step that I need to do in order to get three linear factors, and that is to factorize that quadratic bracket. So the factorized version of x squared minus 10x plus 21 is x minus 3, x minus 7. And of course, you can now prove that those three are factors by taking the values of minus 2, of 3, and of 7. And if you place any of those values of x into the original cubic, of course, you will get an answer of 0. And you can spend a bit of time practicing that if you wish. I would like to say at this juncture that you didn't need to consider the x squareds earlier on. You could have considered the x's. So if you just go back up to near the top where we've got our expanded form, we've got 21 x's and we've got 2b x's. And if we add those together, we know that it would have to equal the 1x that we see in our original expansion. Or if you just consider the coefficients, 21 plus 2b would have to equal 1. And if you rearrange that equation, you get b is minus 10 once again. So it's fine to consider the x squareds, but you could also look at the x's as well. In fact, you could look at either one of those and then use the second one as a check to make sure you've done it right. But at the end of the day, if you look at your three factors, if you find the values of x that make those brackets equal to 0 and replace them into the cubic, you will find that they all equal 0. Okay, good. So now that we've looked at that one example, it's your turn to practice that skill again. So here we've got 8 cubics. They're all slightly different from each other, and you'll realize that when you're working through them and coming up with your solutions. But I would like you please to fully factorize each of these cubics, and that might mean that you get 3 distinct linear factors. It might be that you end up with some repeated factors, or it might mean you get a linear factor and a quadratic factor, and that's as far as you can go, because then you can't do anything more with the quadratic because it doesn't factorize. So I shall leave you to have a go at these. Pause the PowerPoint, have a go, and then when you're ready to get the answers, you can press play again. Good. So in our first one, we get 3 linear distinct factors. They are x minus 1, x minus 2, x minus 3. In part B, again, 3 distinct factors. They are x minus 1, x plus 3, x minus 3. Again, in number 3, we've got 3 distinct factors. They are x plus 5, x plus 2, x minus 3. Now D is quite interesting because you'll notice there's no number on the end of the cubic, sorry. So the first thing we could do is take x out as a common factor to start, and that would be as if we have a bracket x minus 0, and then you could factorize the quadratic that's left. So the x minus 0, or just x on its own, is the result of me taking it out of the original cubic, and then that leaves me with a quadratic that factorizes to give x plus 1, x minus 2. In number 5 is our first example of a repeated root. So we have x minus 1, x minus 1, x plus 3, or if I want to simplify that fully, we would write it as x minus 1 squared. In F, you'll notice that there are no x squareds. Now, when we are using the method that I've just shown you, what I would do personally is when I'm writing that cubic out, I would write it as x cubed plus 0x squared minus 7x plus 6. It makes things a lot easier when you're then deciding on your values of a, b and c. So I would always replace any missing terms with either 0x squared or 0x if it was the x's that were missing. And it results in 3 distinct factors, x minus 1, x minus 2, x plus 3. In number 7, we can find that there is a linear factor of x minus 1. I can find then the values of a, b and c for the quadratic, and I get x squared plus 4x plus 5, but that quadratic does not factorize. So I'm going to leave it as a linear factor and a quadratic factor, and we'll look in another presentation about what that actually means in terms of the graph. And then finally for h, the only difference in h is that there is a 2x cubed rather than a single x cubed, but the method is exactly the same. You find one linear factor, you then find the quadratic remainder, and then you factorize the quadratic at the end. And your 3 factors are 2x plus 1, x minus 1, and x plus 3. So if you got all of those right, then really well done. You have mastered that skill. Okay, so there is one more slide on this presentation, and that, as ever, is to complete your final exercise, which is practicing the art of factorizing cubics using the non-trial and error method that I've just shown you. So on page 25, exercise 4.4, any problems, speak to your teachers please, and they will be able to point you in the right direction or tell you whether you've got something right or wrong. Yeah, so well done on completing your remainder theorem and factor theorem work. I will say goodbye for now and see you on the next presentation.